All right, welcome to ETD 59. Goal is to be to draw, define these S words, solute, solvent, and solution. And what are the four main factors that impact the rate of dissolving and why? Think top ramen, like a true college student. Pause your play and write down the questions. Try to answer them on your own just like we would in class, and then we'll go off them together. All right, now you've hit play again. We can see basic ideas we should write down. This is all about making KoolAid, right? Imagine the KoolAid man bashed into the room right now and spilled his guts everywhere. It'd be awesome. If we look at that, of course, the KoolAid man himself has got this lovely stuff inside him called the solute. That's this thing that's being dissolved. That's the sugar and the KoolAid that are inside of him, the mix. When we add a solvent to that, that's the thing doing the dissolving. And in most cases, for us in our class, it's going to be water, but there are other solvents too. So solute, thing being dissolved, solvent, thing doing the dissolving. Put them together and you get a solution. Now this is a homogeneous mixture of the solute plus the solvent, right? The key thing that we should notice is making a mixture is not a chemical reaction. So if we look at this on the basic level, here we've got this lovely beaker. Inside of it, we've got this stuff called the water. That's my solvent. Inside of that, of course, mixed in between it in the parking spaces that are there are my solute. It could be salt, it could be anything like sugar, right? And together they make a solution, but just as with KoolAid, we can't actually see the particles of solute, so it is a homogeneous mixture. To dig further into that, we should recognize this is a crystal lattice. This is salt, and salt comes in little tiny squares, little cubes, because it's held together by its charges, ionic bonds. That means the only thing holding it together is the actual attraction of the charges. So if you step on it, you break those bonds, and you can hear the crunch as you do that. You can also cheat and take that very same salt, throw it into water, and it will dissociate, which we talked about ad nauseum in the first part of this year. The kidnapping is the ions being ripped apart by Mickey Mouse. They go aqueous when they go into solution, and they become their separate ions charge. They're also known as electrolytes, which is talked about in the TLW a lot. The kidnapping of the salt is the dissociation of it as it goes in, and it makes this great stuff called salt water. Now the water is going to surround it. Mickey's positive ears surrounding the negative parts, the negative ions like chlorine, and his negative chin attracted to the positive things like the sodium, right? So the ears are positive, the chins are negative. Always see oxygen, think hog. In addition to that, you should ask, okay, what's the difference between a homogeneous and a heterogeneous mixture? If we were in class, I would show you two beakers. One beaker would have red dye, food coloring, and water. And it looks nice and pure and like it's just totally red, just like KoolAid. The other one, I have a bunch of red marbles inside of water. You can see the individual marbles. Beaker A would be a homogeneous mixture. That's because homo, of course, the prefix means the same. So they look the same even though they are separate things because they're all mixed together, right? That's a solution, a homogeneous mixture. If we look at the marbles in the water, you can see them and tell them apart. They are different. That's what hetero means. It means they are separate parts. Common heterogeneous mixtures that we see are things like concrete or milk. If you even look at it under a microscope, you'll see little tiny globules of fat. That's because it's a heterogeneous mixture. A colloid is one type of those, right? So most of our unit's going to focus in on solutions, homogeneous mixtures that you can't see with your eye, but you have to be able to see with your mind. Now, there's four factors that impact the rate of dissolving, and those four factors, of course, you can think of all of them if you just think of top ramen, and we've all made top ramen. So the four biggest factors that affect the rate of dissolving. And these ones you already know because you cook top ramen. And if we look at the top ramen, one of the biggest things you can do, you can increase the temperature. If you increase the heat, then what happens? That means that particles speed up. If you increase the speed of the particles, just like in our gas laws, they're of course going to collide faster. And if I increase the number of collisions, that's going to make them mix together faster. A second one that you can do, and it's the first thing you do with your top ramen, if you want it to, of course, work really good, you break it up. You expose a greater surface area, right? If you take that top ramen and you just throw it in there, it's going to cook. But if you want to cook it faster, you can take that whole brick of the noodles and break it up into smaller packets. And then, of course, there's more water to collide with it. So actually increasing the surface area increases the chance of collisions because this is all about collisions, right? Third part, of course, is you could increase your stirring. If you stir, you're basically allowing it to increase the number of times it can collide with the solution that's there. That'll help it go into solution faster. The last one, of course, is the only one that doesn't really have to do with collisions. Not only do they have to collide, they have to both hit and stick together and be attracted to each other, so you could increase the polarity, the amount of charges that are there. That's why, of course, we cook this stuff in there. This increases the attraction. We cook it with water because water has lots of charges. This increases their ability to use the kidnapping trick, right? So collide and actually hit and stick. If we look at the biggest part of that, of course, you've got the noodles there. The noodles are made out of starch, and they will slowly mix with water because starch is long chains of sugar, which is also polar. But you also take that disgusting flavor packet, which used to be loaded with monosodium glutamate and other salts. And the flavor packet, of course, being full of salt, is ionic, so that has high polarity to it. That's why it mixes in there so well and destroys your kidneys as it's doing, right? So if we look at the two major themes of this, one thing is, if you're going to increase the collisions by stirring it, increasing the temperature, and exposing the area, that's why we stir things, heat them on stoves, and, of course, chop them up like chopping up a potato. And then we can cook things in water because that'll increase the polarity of those two things, or mix some salt in and get even more ions into solution faster. So one thing you should notice is about colliding and also sticking in solution. Charges. Hey, we've been talking about that all year. Normally in this part of the class, we would take a look at the questions on TLW 15.1, and we would go through the questions that you had questions about and figure out the MVPs of those. You can ask those questions, as one of the students already did in the last meeting, to take a look at those on our next Wednesday meeting. It's always going to be from 12 noon to 1 p.m. as long as we're remote. The other part I wanted to show you was this salts and solubility that we did the class before, but it's very handy for getting the idea of these things like solute and solvents. If I shake this, of course, my salt is my solute, and my water is my solvent. And now I've made a solution. Hey, look at that thing. It's a homogeneous mixture to your eye, but here we can actually see the individual parts. The parts it's not showing is the water itself. Now, you'll also notice a crucial thing. If I add more solute to my solution, it gets more and more salty. We'd say it gets more concentrated. Now, as it gets concentrated, eventually I'll shake so much salt into here that I'm filling up that parking lot, because that's what the water is. And you'll notice that at a certain point, the salt starts to clump on the bottom and doesn't mix anymore. We would say that we filled it with as much solute as we possibly could at this temperature. That means that it is saturated. So this is a saturated solution. And one of the nice things about the saturated solution is I can see that there are some cars parked on the side, the ions parked on the side, because there's no more parking spaces that are left. Now, if I drain away that fluid, you will notice a crucial thing. It drains away both the solute and the solvent, but anything that wasn't in solution remains. And what you end up with is a whole bunch of solid salt stuck in crystals. Hey, let's dig that up and put on our French fries. But that's what happened to a bunch of oceans and lakes as they evaporated away and left behind salt lakes, a bunch of salt, which we could then collect and put on our food. Usually we dig it up out of the ground because they're buried, right? Solute. Hey, the Great Salt Lake. The other part of that, of course, is to recognize that there are different types of salts. And if I shake this one in called strontium phosphate, you'll notice that it goes in a solution. It likes water. It's soluble. However, if I give it a couple of shakes, you'll notice that, oh, look at that. I can't fit any more in. It's not going in the solution. It's already saturated. So different salts have different solubilities. And all salts, of course, all things are slightly soluble, but some are more soluble than others. Everything likes water because it has strong charges. But even insoluble things, like strontium phosphate's not that soluble, they're still soluble a bit. You can see they get saturated quickly. The other part of this, of course, is to make sure that you understand how this affects the real world. If you go to Solute, you find the Great Salt Lake. Basically, it's just like the TLW asking, okay, I got a salty solution. If I leave it out and the water evaporates, what's it leave behind? It leaves a bunch of salt behind, but it also makes the rest of the lake more concentrated. It's got more solute and less solvent. And that's why it's such a salty place, and you can swim and float pretty well, and there's just nasty flies there. That's also why the Southwest has lots of cool formations, because there was a bunch of salt water in a giant sea. As the sea went away, it left salt deposits, which absorb some water and causes them to crack. So you can see cool places like Arches. So Solute. Hopefully you got the idea of the 4 factors that affect the rate of dissolving: increasing surface area, increasing stirring, increasing heating, because those all increase collisions, and, of course, polarity. That's why so many wonderful things go into the water, and we cook with water as well. You hopefully also have the understanding of what a solute is, the thing being dissolved, what a solution is. It's a homogeneous mixture of that solute inside a solvent. You can't see it. Cool.